Hi, I'm Mr. Putnam. Welcome to Physical Science week number 1. We're going to start off reviewing some things about how this class works, and then we're going to look at atoms, kind of our first topic for this class, and then we're going to do a little experiment today with a glass of water. Cheers. So in this class, I'm going to ask lecture questions throughout the class. Usually there'll be about 5 of them in each class. And what you're going to do is, for your notes, as you're taking notes, you're going to write your answers down to those lecture questions. That's one of the things you'll include on your discussion post for each week. Then you'll also start some questions about the lecture and sort of pose them to your fellow students. And we'll talk about that a little more in a minute. But this is the first lecture question of this first class, which is, what is happening chemically to the methane in this water? Now, you might not normally think there's methane in your water that you could light on fire, but in certain parts of the country, there have been instances recently where people have been able to light their tap water on fire. Very frightening, I know. And that's usually because they're on a well, and the thought is that that well has been contaminated by natural gas. Oftentimes, natural gas that's been released from inside the earth because of a process called fracking, which is one of the ways we get natural gas out of the earth. Now, of course, that's a frightening prospect, but for what our purposes here, we're just going to be talking about chemistry. So what do you think, and you can say, anything, but I want you to sort of answer these questions as best you can. What do you think is happening chemically to the methane in this water? Now, we're not talking about the water, just talking about the methane that's here. When you light methane, or natural gas, methane is the primary component of natural gas. When you heat it up and light it on fire using something like a lighter here, what causes it then to combust? Or what might be happening chemically to that methane to make it combust? How is it changing? Now, you might not have a very good answer to this question, and that's okay, because sometimes I know you won't. But I'd like you to give your best shot at answering the question. You can even pause the video now so you can write it down. And hopefully you cannot light your water on fire. Well, this is what's happening chemically to the methane in your water. Now, methane by itself looks just like this. It's a carbon atom bonded to 4 hydrogen atoms, and they follow each other around. They stay connected to each other until something happens, until there's enough heat that it can separate them. And that's what that initial heat given by the lighter is. Once that happens, though, they can actually supply its own heat because the separation actually reduces or produces heat, which can be used to sustain the burning, which is why once you light it on fire, it can keep burning until you run out of methane. Anyway, that causes or allows methane to recombine with the oxygen that's in the atmosphere to form new chemical substances. So the oxygen might combine with 2 of the hydrogen atoms to produce water. And the carbon atom might combine with a couple of the leftover oxygens to produce carbon dioxide. In fact, most of the time when you're burning or combusting a fossil fuel, like natural gas, this is what you're doing. Out of your tailpipe in your car, most of what's coming out is just water and carbon dioxide. In fact, I suppose you could start your car and put a plant behind it, and your plant would be very happy because plants need carbon dioxide and water as the primary 2 ingredients for growth. So that's what is being produced when we burn methane or when we burn other things, other fossil fuels like gasoline, heavier hydrocarbon molecules. All right, so that's kind of the beginning. I'm just kind of giving you a little teaser, a little taste of some things we'll talk about. Try to remember this, but we'll be talking about this more. And I'm just trying to give you a little idea of some of the things we're going to be going into as we discuss chemistry. I am Mr. Putnam, and I like to eat spiders, and I approve this message. Not really a big fan of spiders. There just happened to be one hanging down in front of me recently, and so I took a picture. Hi, I'm Mr. Putnam. That's my way of introducing myself. These are some things I like to do, just to tell you about myself. I like to play Ultimate Frisbee. Um, I like music, especially this guy. Extra credit if you know who this guy is, the greatest guitar player of all time. I like reading up on the news. I'm not like always the best about it, but I like to stay caught up on what's going on in the news. In fact, I hope to subscribe to The Economist again soon because it's a great magazine. And I like spending time with my family. I'm now up to 4 kids and 1 wife, and that's probably a good way to keep it. You don't really want to have that the other way around, I don't think. And I think we might be stopping at 4 kids. That's, maybe too many. So that's what I do. That's what I spend my time on. This is what you'll be spending your time on for the next several weeks. So, we've already talked about, or hopefully you've already done the introduction where you've seen that you'll be doing lessons using class notes, and I'll show you how to set up those class notes. And you'll also be doing some scientific method assignments or lab assignments that I have in each weekly module. But you'll also be doing lecture discussions, and that's going to be 30% of your grade. So it's a substantial thing, and all that involves is just doing what you're doing right now, watching this video, and then discussing these lectures with your fellow students, which allows me to give you a reduced homework load. So there are 3 components to each of these lecture discussions that you're going to input. One is you're going to provide your initial answers to the lecture questions. You've had one already, which was what you thought might be happening to the methane in that water. Then you're going to ask 2 questions to prompt discussion with your peers. Those questions, I'd like them to be connected to the lecture, but they can be creative questions. They can be questions about, how you feel about something. You can ask questions like, I don't understand this. Can you help me understand this? Or they could be a question like, what if this were true? Whatever, it can be creative. But I'd like them to be connected to the lectures and also hopefully connected to helping other students learn or think about things maybe in a different way than they have before. And then, of course, once you've asked those questions, I'd like you to respond to at least 2 of those questions that have been posed by your peers. Here's the sort of homepage you've probably landed on and seen already. You can obviously contact me using that information there and review any of the things about how the class works by reading the rest of the information on that homepage. And this is what a weekly module will look like. At the beginning of each module, you'll have a learning and objectives assignment. For the first week, it's actually going to be worth some points, but this is going to have videos, supplementary materials that can help you, and also show exactly what you're trying to master, what you want to learn, or what you should learn in this weekly module. And then you'll have some lessons that will have questions that will go into your notes document. And you'll have to begin filling out the notes document and filling in the blanks, answering the questions that are there. And then the assignments that start with numbers like this are going to be what I call scientific method or lab assignments, where you're working on the steps in the scientific method, learning how to think like a scientist. And then lastly, you'll have a lecture each week and then a lecture discussion. Sound good? You guys ready? You guys excited? I bet you are. I bet you are. So your class notes, I have a document or a section in here where you'll have to set up your class notes, and you've probably already done that as well. If you've had trouble or need help, let me know. But basically, you're just going to take this assignment, the assignment that I have here, or the template, I guess, that I have there. You're going to rename it. So you're going to make a copy using that screen. Then you're going to rename it, not using my name, but using your name. So it'll just be PS Notes Joe Smith or whatever. Then you're going to share. So you go to File, Share that document with me so that I can then see it and review it and grade you on your notes. So you're going to then add my email address, jputnam@summitlc.org, to share those notes with me. All right, this week we've done our introduction. We're going to talk now a little bit about atoms, and then we're going to do a little experiment. Here are some words for today: matter, density, ions, and isotopes. here is a sort of list of what we're going to do for the first semester or trimester of this class. So we're going to focus on atoms, molecules, and then energy, which tends to be released or absorbed often in the bonds of these molecules. So that's why these two are kind of connected. So atoms, molecules, which are groups of atoms that are bonded together, and then energy. So what is matter? Kind of a fundamental concept of what the nature of reality is, right? What is matter? Well, you might say that matter is everything, but that's not quite true, because there are things that you can talk about that aren't matter. Now, anything that is an object, or that we'd say this is an object, like I'm going to pick up this object, or I'm going to show you this object, a 9-volt battery, is matter. It has mass and it takes up space. That's how we define what matter is. Now, there are a lot of things that would then count as matter, right? Pretty much any object you can think of. But you could also come up with things, maybe abstract nouns or things like that, that aren't matter. So for your next lecture question, I'd like you to think of something in the world that's not matter. And it can be, and hint, abstract noun might be a helpful thing to look up to find out, to think of something that is not matter. Is there anything you can think of that does not take up space and have mass? Because everything around you that you can see and touch and feel is made up of matter. Matter has three states, solid, liquid, and gas. So again, I'd like you for your second lecture discussion question to write down something that is not matter, a thing, or something, or whatever, an abstract noun that is not matter. Keeping in mind that everything you can see and touch and feel is matter because it has mass and takes up space. Of course, solid, liquid, and gas, the three states of matter, hopefully you've heard of those before. In solids, the atoms or molecules of the element are sort of lodged into place. They might vibrate. In fact, that's what can make them very hot. In fact, the reason why when you touch a hot, pan on the stove and it burns you is because the molecules are vibrating so fast that they vibrate the molecules in your finger, and that vibration is what causing burning, damages the skin of your finger. Well, in a liquid, those molecules are close together, but they're free to move around, to sort of slip past each other. That's what makes a liquid a liquid. They're not stuck in place. And then in a gas, the molecules are much farther apart. They don't have any forces sort of keeping them close together, and they are able to sort of be liberated from their neighbors, although they bounce off them quite often. And matter is composed of atoms. So all the things, again, that you can see around you that have mass and take up space are made of atoms. And this is what all atoms basically look like. They have this basic structure. 8 protons, 8 neutrons, and 8 electrons. Oops. And a couple things about the atom. You're going to be going over these soon, or you already have in some cases. The protons have a positive charge. And so just like a magnet or something like that, they would tend to repel other things that have a positive charge, and they would tend to attract things that have an opposite charge. Well, their attraction for electrons, which are sort of these, I guess, I should do a different color maybe, which are these red things, their attraction for electrons, the negatively charged particles here, is actually what keeps the electrons near the atom's center. So these opposites are attracting, but the electrons have so much energy that they don't really get sucked in or, attached to the proton, because they are moving at incredibly fast speeds. And then there are the neutrons, and the neutrons have no charge. They are neutral. I guess I'll just draw a circle. So they might be the green things here, it might be the neutrons. The blue things might be protons, and the red things might be electrons. So the protons and neutrons are inside of the center of the atom. They're not really inside anything, they're just at the center of the atom. And they are known together as the nucleus. The protons and neutrons make up the nucleus of the atom. Nucleus meaning like the center. And now these atoms can bond with each other. One thing I'd like you to note is when you touch something solid, it feels pretty solid, right? It feels like you're touching something solid. But the outside of every atom, of every bit of matter in the entire universe, is these electrons that are actually flitting around and moving at extraordinarily fast speeds and simply have a strong negative charge. That's not a very solid seeming outer layer of all the stuff that makes up your hands, right? Kind of strange. Well, we'll be looking into how that works soon, but I'd like you to think about how that could possibly work for the time being. All right, so these atoms then can combine with other atoms by, in this case, sharing electrons and form molecules. You can see this is actually a water molecule. We'll be destroying one of those water molecules later in class. We're going to be destroying this water using nothing more than a 9-volt battery. Well, thinking about that structure, a nucleus with protons and neutrons in the middle and an outer layer of electrons, I'd like you to think about basically relating that to something the size of a football stadium. If you expanded a single atom, these tiny little atoms, till it was the size of a football stadium, how big do you think that nucleus would be? Those protons and neutrons. That is your third lecture discussion, or lecture question, I guess I should say. How big do you think the nucleus would be? Would it be, say, the size of the grass in the middle of the stadium, like the field there? Would it be the size of maybe a 10-meter sphere? Would it be the size of just one of the people on the field out down there? Or would it be even smaller? So go ahead and answer that question before, or actually push pause and answer that question before I go on and tell you how big the nucleus of the atom is. Here's an atom. You can see it kind of being blown up. You can imagine maybe the nucleus being about that size, whatever that is. Almost the size of the field, I suppose. But the truth is that the protons and neutrons, if you blew up the atom to the size of a football stadium, would be about the size of a pea, or maybe a blueberry, in the middle of the field. Extraordinarily small by comparison. Yet, the protons and neutrons make up all the mass of the atom, which means that all of the mass of the atom, all the weight that it would have, is due only to this tiny little thing in the center of the atom, which means that mass is extraordinarily compact. It's extraordinarily dense, and the rest of the atom is actually empty space with these tiny little insignificant electrons. They're much smaller than they appear in this picture, flitting around the outside. And they weigh almost nothing compared to the protons and neutrons. Well, that gives rise to some very interesting things in the universe. If you could overcome the forces of the electrons that are keeping atoms separate from each other and put nuclei together and sort of build this huge nuclei where you just have the dense center parts of the atoms, then you could have something like a neutron star. Neutron stars are incredibly dense. They're dense on a level that we can't even fathom. A neutron star, basically the entire weight of a 747 Boeing jet, would fit into his teaspoon, a sugar cube, basically. The entire mass of a 747 jet. And that's because you're putting all these nuclei together. So I want you to think about these two things. First of all, the atoms are extraordinarily small, but the actual mass of the atoms is even, by comparison, even smaller in how little of the space it actually takes up. So it's extraordinarily dense. And if you can overcome that, creating what's called a neutron star, where basically all you have is a nucleus with no other empty space or electrons flitting around, you just have a large, built-up, extraordinarily big nucleus. You can then get some very interesting things in the universe. Now, I just brought up the concept of density, so I want to review that with you really quick. Density is mass over volume, and you now are part of the density gang. And for your fourth lecture question, I'd like you to tell me that you have done this sign. You've actually physically performed this. You can even take a picture of yourself if you like, but you don't have to. But you've learned how to do the density gang sign, which is mass, m, over v volume. Density is how much mass you can get into a volume, so it's mass divided by volume. Mass per unit volume, which means if you have 50 kilograms in a 1 meter cubed volume, that means you have 50 kilograms per meter cubed. Every meter cubed would weigh 50 kilograms. And the denser something is, the more mass you can fit into a particular volume. So mass doesn't really have to do with size, except that it tells you how much weight each bit of something would weigh. So the units of it in the metric system, or the standard, the international system that we would normally use, are kilograms per meter cubed. So again, for your fourth lecture question, you're going to tell me that you have performed the density gang sign. So that you'll always remember that density is mass divided by volume. How much mass you can fit into a given volume. Well, we've learned about atoms, and I'm going to tell you one more thing about atoms before we do our little experiment. And that one more thing is that atoms come in some different varieties. Now, the only thing that differentiates all the different atoms in the universe from each other is the number of protons in the nucleus, which is kind of a shocking thing. It means that the only real difference between, say, oxygen and carbon and, say, arsenic, or something that's poisonous, or neon, something that's often a gas, or iron, or gold, is simply the number of protons in the nucleus. All the vast variety of properties of different elements and what we can use them for is all based on just the number of protons in the nuclei of the atoms of these things. Well, that dictates what the actual substance is. So 8 protons is always oxygen. It's never anything else. But you can vary, even if you have 8 protons, or whatever number you have, whatever substance you're dealing with, you can vary the number of electrons or neutrons. That's going to give you some different varieties of the substance. So for example, if I added an electron over here, you'd notice a couple of interesting things. First of all, you'd notice that now that you have 9 electrons instead of 8 electrons, you're going to have an imbalance in charge. It means you're going to have 8 protons, 8 positively charged protons, but you're now going to have 9 negatively charged electrons, which means you're going to have 1 excess negative charge, 1 extra negative charge. Well, anytime that you have a charged atom that has a difference between the number of electrons and protons, whether it has more electrons or fewer, you're going to have something called an ion. And it's going to be overall electrically charged and want to, be attracted to things that are oppositely charged or repelled from things that have the same charge. So that's an ion. Now, the same thing can happen with neutrons. You can have a different number of neutrons or different numbers of neutrons. Oftentimes, you don't have the same number of neutrons as protons, and it's not important that you do. But usually, atoms come in different sort of flavors of varieties in terms of the number of neutrons, and that gives them slightly different properties as well. So you might have 9 neutrons in oxygen, or you might have 10, which means you might add, in fact, I guess I'll add another ball in here to show that. So this adding another blue ball in the nucleus means now I have 9 neutrons in the nucleus. I might even have another one and have 10 neutrons in the nucleus. Now that's the different numbers of neutrons gives you a different weight because, again, these protons and neutrons are what gives all the weight to an atom. The electrons are so light they don't matter. So it adds a different weight, and it adds a slightly different set of properties to the nucleus. So we call those isotopes. And ions then have to do with a change in charge, while isotopes have to do with a change in weight. And that is the kind of the most important thing to remember when you're thinking about atoms that make up the universe and the different varieties of atoms you might have, is remember 3 things. The number of protons tells you what substance you're dealing with. And then ions and isotopes can give you different varieties of those substances. So an ion could have a charged, it could be charged, and therefore it would be attracted to or repelled by other charges, whether they're like or different. And isotopes would give a different weight. So those are sort of different flavors of, say, oxygen or carbon or helium or whatever the substance might be. All right, all right. And then we then categorize these substances on something called the periodic table. And you'll learn more about this soon, but for now I just want you to see that the periodic table has been lumped together in such a way that elements that have the same number of electrons in their outer shell are all in columns. So that's what's true of all these things in this column right here, for example. And you see that as we lump things together this way, that these electron configurations, things tend to have similar properties. So we have things that we call halogens because they're reactive, and they all tend to be in the same group. Or the nonmetals or semimetals all seem to be kind of over here, right? The metals, the alkali and the earth metals, are all over here, and then there's the transition metals and all these different things, and we kind of give them different colors. In fact, they even have properties that are similar, so that when you look at, say, a periodic table and think about a specific temperature, like in this case 322 degrees Celsius, 595 Kelvin, that's the same way of saying that, or 611 degrees Fahrenheit, you see that certain elements are in a gas state, certain elements are in a liquid state, and certain elements are in a solid state. And they all kind of clump together, right? Like sort of all the gases seem to all be over here. Well, that's interesting. All the solids tend to be more in the middle, right? That's kind of interesting. And then there's a few liquids, like all these tend to be liquids at that particular temperature. Well, that's kind of interesting too. So there's these common properties that these elements tend to share based on where they exist in this table. All right, now it's time to do our experiment. So we're going to do something called hydrolysis, and we're going to actually destroy some water. We're going to do it using a battery. So water, of course, is H2O. You can see that here. 2 hydrogens, which are bonded to an oxygen. So all that's in this water is hydrogen and oxygen. Now, if you separate those two things, you create a gas, right? Hydrogen exists as a gas normally at room temperature, and so does oxygen. But when they're together, they're in liquid form. So let's make sure that you guys can see this well. I'm not even sure how I can see that right now using the program I'm using. But hopefully it'll work out okay. So I'm going to take this 9-volt battery. I'm going to touch the terminals, the cathode and the anode, to this old power cord that I have here. And then the two sides of it are going to be here. By the way, if you ever lick a 9-volt battery, woo, get a nice little shock on your tongue. It's kind of fun because your tongue allows the electrons to actually pass from one terminal to the other. The moisture and the salt kind of helps with that. All right, so I'm going to put these things in the water, and I want you to observe what happens when I do so. Here we go. So hopefully you can look in closely. Because what's happening now is I've powered these two terminals. I've put a positive and a negative charge on, well, I'm actually having trouble holding it, unfortunately, on both ends of the terminal, which means that there's, just like through your tongue, electricity is able to flow from one terminal to the other. You know what? I need to add some salt to this water. It's going to help the electricity flow a little better. I'm going to pause the recording and I'll be right back. Okay, I'm back. And I've got this working a little better now because I got some salt in the water, which helps the electricity to flow between these two terminals a little bit better. So the electricity from this 9-volt battery is now flowing between these two terminals, and I want you to look and tell me if you see anything on the terminals. Anything collecting or anything rising from these terminals. And you might see it happening more on one terminal than on the other. Well, what's happening and what happens in this process is that the hydrogen in the water is separated from the oxygen as electricity flows through it. And so on these terminals, hydrogen gas is being collected on one and oxygen on the other, because they tend to be attracted then one to the positive and one to the negative terminal because they become ions. And that is what is happening here. And you can see the gas rising. Now, why do you think there's more gas rising on one of these than the other? Why would that be the case? And hopefully you can see it. That's going to be your 5th lecture question, is why do you think there's more gas or more bubbles coming off of one than on the other? In fact, usually you can see some bubbles. You can hardly even see any bubbles being created on the one. And the reason has to do with how much of the gas there is. How much of the substance there is. And that is kind of the point of this experiment, is you can see a lot more hydrogen than oxygen. The bubbles of hydrogen are bigger or more than the bubbles of oxygen because there's more hydrogen. Every time you break apart one molecule of water, you get 1 oxygen atom and 2 hydrogen atoms, because matter combines in simple fixed ratios. That's how matter always combines, because any time that you're putting hydrogen and oxygen together to form water, if there's any excess hydrogen or excess oxygen, it's just going to go away because it's not going to stay in the liquid form with the water. It's going to go find someone else to combine with. And so matter always combines in these simple fixed ratios because matter always combines in molecules like this. And we'll be learning more about molecules at the end of class, but I just wanted to show you today how that works and that principle, and we'll actually see more about that when we get into the molecules section of the class. So thank you for coming to class today. So here's how the question, and I guess I'll ask this actually will be my 5th lecture question, which is, if I do electrolysis on a cup of water and separate out a gazillion oxygen atoms, then how many hydrogen atoms had to be separated? How many hydrogen atoms would it take, would be pulled away to get a gazillion oxygen atoms? How many hydrogen atoms would you have pulled away on the other side? That's basically the question. And you should remember that the answer has to do with cookie dough, because there are fixed ratios of hydrogen to oxygen in water. It's not sort of a fungible thing like cookie dough where you can have lots of chocolate chips or just a few chocolate chips, but you still have cookie dough and it's still going to make cookies and they'll still be yummy. You have to have exact ratios. You always have exact ratios when you create these substances because they combine at the smallest level with each other. So molecules are not like cookie dough. Thanks, guys. Have a good week. And let me know if you have any questions.